Right, hello everyone, and welcome to the re-recording of the Programmable Networking and Testbed Integration tutorial at the 6th Annual National Research Platform Workshop, 6NRP, that was held at the San Diego Supercomputer Center at UCSD on January 28th of 2025. My name is Mohammad Sada. I work here at UCSD, and along with me presenting the tutorial was Justas Balcas from ESnet, who is a software engineer that works on the ESnet project, which is very fundamental to the topics that we're going to be talking about today, especially in what pertains to network experiments and conducting those experiments on the National Research Platform and the Nautilus cluster. Let me begin by saying that the slides can be publicly found on GitHub and on the 6NRP website. You can find them on github.com/nrp-nautilus/6nrp-smartnik. If you go to github.com/nrp-nautilus, you'll see a bunch of repositories, and some of them are 6NRP tutorials, and one of them you'll see the SmartNIC one, which will have the slides we'll be going to be going through, as well as all the experiments that we're going to be conducting, plus others that we're not going to have time to go through, but you can reproduce on your own. And we're always more than happy to get any questions you might have and help you get started. The first thing we want to talk about here, and the main topic here, is talking about SmartNICs, and this is to shed the light on what resources are available on the cluster and what sort of hardware and software the users can use to conduct their networking experiments on NRP, as well as integrate with other existing network testbeds and research testbeds, and make use of the wide variety of hardware that NRP and Nautilus have to offer, especially when it comes to networking. So normally when we talk about hardware, especially in the context of Nautilus, hardware is always grouped in terms of the CPU, memory, GPU, and sometimes even FPGAs. But there's plenty of network components that often get overlooked, and those network components are there and available for experimenters, for users, for research groups to use them in all sorts of experiments they're carrying, whether they're of a network nature or whether they can benefit from having a network factor to them, especially with the rise of all sorts of HPC, AI, and ML applications. Networking is a topic that cannot be neglected, and knowing what sort of resources is available is a fundamental part of effectively using the cluster. So SmartNICs, when we talk about SmartNICs, of course, NIC is a network interface card. SmartNIC is a smart network interface card. So what they differ from traditional NICs is that they're advanced cards that offload all sorts of tasks from packet processing and security and storage and other tasks from the CPU and from the host node onto the cards themselves, and therefore freeing up the CPU to carry out other tasks, as well as improving latency and conducting all sorts of edge programmability, especially when we talk about using FPGAs as SmartNICs, since FPGAs are fully programmable hardware. Having those smart network interface cards on the edge allows us to define our own tasks and functions that these cards can carry out and offload not only from the CPU and the node itself, but also offload from the core of the network, from the switch to the edge, sort of adding an edge programmability by conducting our full programmability. And we, of course, have to talk about what is available on the cluster. And the first thing we need to talk about is the ConnectX-6 SmartNICs. So as you probably know at this point, the National Research Platform is mainly one large Kubernetes cluster that spans across many countries, many campuses, and R&D institutes, and it it consists of nodes. So the servers we use, the hosts are Kubernetes nodes, and each one of these nodes is connected to the network through a SmartNIC, basically, because in most cases, each one of these nodes has a ConnectX-6 card, and that ConnectX-6 SmartNIC has a bidirectional support for RDMA, which is remote direct memory access, and has two ports, and each of these ports is 100 gigabits per second. And of course, one of these ports is what plugs the node onto the network, and it's used for deployment purposes. But the other node is always free and there and available for research. Uh, Especially, for example, here at SDSC, many of the Kubernetes nodes are plugged in through both ports. One port, like we said, is used for deployment reasons, so odds are you're not going to be able to use this port effectively for conducting meaningful workloads, but the other port is available, and you can use that port as 100 gigabits per second. In most cases, some nodes have even higher bandwidth cards for network research. And you can attach it to your Kubernetes pods and use it in your experiments using various tools like Multus and ESnet Sense, which we're going to be talking about. And of course, this card offers other features like virtualization features, so multi-tenant, so multiple users can use the same card, sort of split it or slice it and use it in their experiments at various bandwidths. And of course, it allows for other work using other applications like VPP, which is sort of for vector packet processing, which allows us to add another layer of programmability and flexibility in leveraging what the card can do in terms of packet processing, and of course using DPDK, which is short for Data Plane Development Kit, which is software that allows us to also write our own packet processing logic and write our own DPDK applications that bypass the kernel, which allows us to conduct applications at line rate or almost line rate, achieving very low latency and very high throughput. And going from the ConnectX-6 SmartNICs, we have to talk about the NVIDIA BlueField 2 SmartNICs. So when we talk about the ConnectX-6 cards, many people like to regard them as NICs and not smart NICs because when compared to Bluefield 2s have high level of functionality. They have all sorts of applications. They're more powerful cards. Of course, they're smart NICs and DPUs, and they have plenty of ready available uh, offloading functions that can be loaded onto the SmartNIC and used almost instantly, leveraging that programmability with tasks like storage, networking, and security. Of course, they're very capable, very powerful. They have their own ARM cores, and of course, like the ConnectX-6 cards, we have many cards that are 2 by 100 gigabits per second, and we have 7 of these Bluefield 2 SmartNICs on the Nautilus cluster. The other thing we need to talk about here is the availability of Tofino 2 P4 programmable switches. So all of our nodes on the cluster, they're behind switches, and many of these switches are P4 programmable because they have Tofino 2 chips. And by being P4 programmable, for those of you who do not know what P4 is it's a C-style language for packet processing. It basically allows any user to write their own even arbitrary packet processing logic and load it onto the switch. And currently, we are working on a project that would allow users to use these switches and write their own P4 programmable logic and load it onto the switch, control their experiment from the switch side and the SmartNIC side, and of course, control the control plane entries. And then users will have access to control plane and data plane, sort of create their topology, manage the network, and conduct more meaningful network research. Of course, we going from there and talking about P4, we have to talk about the availability of FPGAs on the Nautilus cluster. So, as we have talked about in various tutorials, various environments, the Nautilus cluster has 32 Xilinx Alveo U55C FPGAs. So those FPGAs, so if you don't know what an FPGA is, it's short for Field Programmable Gate Array, which means it's basically a chip. The FPGA is the chip on a card. When we say FPGA, we interchangeably either mean the chip, which conducts the offloading that is on the card, or the PCI card itself. As you can see here on the picture on the right, this is the U55C card, and of course, Xilinx was bought by AMD, so you might hear it being called AMD Alveo 55C or Xilinx Alveo 55C, but we're referring to the same card here. And of course, that card, as you can see from the picture, also has network ports, so it takes QSFP28 modules. It has two ports. Of course, we can call them Ethernet ports, but here we're talking about uh, completely programmable hardware. So it can be Ethernet, can be InfiniBand, it can be any sort of any packet processing logic and encapsulation and headers that you define by hand. So those cards offer a very high level of flexibility, just like P4 switches do, and they also offer 3 by 16 pin PCIe Gen 3 PCIe connection to the host itself. So FPGAs, like we said, it's field programmable gate array, field programmable as in it can be programmed in the field, which means after deployment. It's fully programmable hardware. Gate array essentially means, sorry, let me get back to the slide. Gate array means an array of logic gates. Basically, in simple terms, what that means is that we have a very highly programmable card that has plenty of resources, including high bandwidth memory and a large number of lookup tables and logic gates and so on and so forth. This allows us to have a very powerful card that we can design our own logic for and use as a smart NIC. And of course, by using it as a smart NIC, we can offload all sorts of network functions and virtual functions onto the card itself. We can write our own applications onto the card that can do all sorts of security applications and sort of risk mitigation and high performance computing as well. We can also write our own AI applications since it's fully programmable. We have full freedom to do whatever we want. So you can combine your smart functionality and packet processing logic with other components that can be conducting very meaningful parts of your experiment. So let's say you're conducting an AI experiment, you can write your packet processing logic to include data processing, for example, that can offload tasks that traditionally are conducted by the CPU and GPU and so on and so forth, and make use of that programmability. And one main thing about these FPGAs is that they're compatible with what AMD calls the open NIC shell. So the open NIC shell allows these cards to be exposed to the operating system and then host as network interfaces that the operating system can see, as well as offering P4 programmability. Like we said, we have the Tofino 2 switches. These are P4 programmable by having FPGAs that are P4 programmable. We can create an environment where we can conduct experiments through our packet processing logic, both on the core of the network, on the switch level, and on the edge of the network. Like we said, we have 32 of these FPGAs, and actually all of them are geographically located here at SDSC. But also all 32 of them are behind an edge core Tofino switch. So having that programmability on both sides allows us to conduct experiments on a much higher level that allows us to have a very high level of freedom in terms of programmability and how our network functions at every single level. And of course, they also have other capabilities. For example, they have full support for VIDUS HLS, which is short for high-level synthesis. What this means is that these cards can very easily program by writing C and C++ applications without having to know hardware design and FPGA, being an FPGA engineer with plenty of experience, because the traditional environment for programming FPGAs involves very low level uh, hardware description languages that require a very high knowledge of the hardware itself and of how it can be programmed and requires a very sort of high experience in that field itself to be able to effectively write a program that can benefit you in your research. On the other hand, if you're comfortable writing C++ code, it's a much smaller step going from there and learning how to write effective HLS C++ code for FPGAs that can benefit you in your research, whether that research is relevant to networking and programmable networking, or it's for other science domain research fields that you might want to use the FPGAs as processing offload cards and processing accelerators to offload all sorts of high throughput, low latency uh, tasks from CPUs and GPUs onto the card because, like we said, they have PCI connectivity, so you can very easily utilize and leverage that to send workloads from the host itself and from your Kubernetes pod that is requesting the FPGA onto the FPGA itself, as well as send workloads through the 2 by 100 gigabit per second connections onto the FPGA. And when we talk about using them as SmartNICs, and we're going to be hosting future tutorials over Zoom to dive deeper onto how to use these FPGAs as SmartNICs, but by using them as SmartNICs and using tools like the ESnet SmartNIC tool stack, it allows us to leverage both connections, both PCI to the host and Ethernet connections onto the switch or onto whatever they're connected at in whatever environment they are to use the bandwidth on both and conduct experiments on a much higher level. And of course, like we said, they have high bandwidth memory. So in many use cases, using them as opposed to using CPUs or GPUs, they tend to outperform CPUs and GPUs, especially when the task at hand is very high throughput and requires very low latency. Now, FPGAs and Nautilus, like we said, we have 32 of these cards. In terms of what nodes they're on, you can see we have listed them here. So they're on node-1-1.sdsc.optcomputer.net, which is a node all the way to node-2-11. As you can see, all of these nodes are nodes on at the San Diego Supercomputer Center. If you go to portal.nrp-nautilus.io/resources, you can see one of the columns says FPGA free and one of the columns says FPGA total. So both of these columns list the FPGAs that are either free or the total number of FPGAs on a node. And if you filter out which nodes have the FPGAs, you'll see that they're the 14 nodes listed here. The nodes that have the FPGAs in green, we have flashed those specific FPGAs with what is called the XRT shell image. So what this allows you to do is it allows you to load your C++ HLS applications that are written for these FPGAs using the Vitis or Vivado onto the FPGAs very easily using the Xilinx tool stack without having to reflash the FPGAs because uh, flashing the FPGA and reflashing the FPGA, of course, requires power cycling. So the ones we have set in green are already pre-flashed with XRT, which allows you to run HLS applications. The ones in blue at the bottom here from Node-2-6 to Node-2-11, these are all flashed with the open NIC shell image and shell that allows users to use them as SmartNICs and use the ESnet SmartNIC tool stack that allows you to very easily have a bunch of tools that you can use to talk to the FPGA as if it was sort of a switch on the edge. So it allows you to use the FPGAs with very simple P4 programmability and, of course, simulate and emulate the behavior of your P4 logic without even before compiling it and even before synthesis and loading it on the actual hardware to probe counters and seeing how the packets are traveling and controlling your control plane on the FPGA itself, as well as plenty of other features that are available with the SNet SmartNIC. And like I said, we are going to be discussing this further over future Zoom tutorials where we can show you hands-on experiments that you can do where you can actually use the FPGA as a SmartNIC and talk to other FPGAs, talk to the switch, talk to network interface cards, and talk to other environments like for example, the Fabric testbed. And now we're going to be moving on to talking more specifically about network experiments on Nautilus and how those can be conducted. So as you know by now, Nautilus is a Kubernetes cluster, which means the smallest unit that you can provision and request resources with. The smallest thing you can do with Nautilus, for those of you who are not very familiar with Kubernetes, is provision a pod. And a pod is essentially what hosts a container. This pod works, if you look here, for example, let's say this a gray rectangle here. This is a node. A node is a physical host, physical server, so it's an actual computer at a data center. And the node hosts pods, and pods essentially are what hosts a container. So we're talking about a Docker container that you can use for your experiments, whether that container is to talk to other containers or let's say that's to conduct whatever experiment you're having. So Kubernetes pods are slightly different from virtual machines, but in many aspects they are similar. So when you run your Kubernetes pod, you select what image, Docker image you're running, and you spawn up your pod. And when you want to conduct network experiments, one of the very essential basic functionalities that you would want to have is having a network interfaces on that pod. So traditionally, when you provision a pod, it adds let's call it a default interface, which is based on the network provided by the node itself. So that interface you see is what provides internet access to the pod itself. But let's simplify this as much as we can. Let's say we have this is one node here and this is one node here. So we're talking about separate, two different physical hosts or nodes, and we're talking about two pods, one on this node and one on this node. And I want this interface, let's say this is an arbitrary interface, to talk to this arbitrary interface on this other node. So I want to conduct an experiment where I can have another interface on the node. I can have a network experiment. And three things would have to be available here for my experiments to be done. First thing here is I need to have the two nodes and the two pods. And the other thing is each pod needs to have the interface. And the other thing is I need to have the path. So in terms of having the interface, how can I attach an interface from the physical node to the pod itself? This is where Multus comes in. And of course, Multus allows us to have multiple network interfaces beyond the default one that we just talked about. And it allows us to do that through what we call in Kubernetes a network attachment definition, or short, we call it a NAD. So a NAD is basically us defining in our YAML what constitutes an interface that can be taken from the physical host, the node, and feed through to the pod so that the pod can use it. And of course, there's multiple types. The easiest type we can talk about is uh, having a bridge interface from the physical host or physical node onto the pod. And from there, let's say we have two pods on the same node. If we have a network attachment definition for a bridge network from the node, and we use two pods that use this NAD, both both pods, each one of them is going to have a different interface, and those interfaces will be part of the same bridge network if I define it to be so. And then I have two distinct pods that can talk to each other onto those two interfaces that I defined. This is very simple, very easy to implement because we're within the scope of the same pod, within the scope of the same node. So the network traffic isn't traveling outside of the node. So the bridge traffic is the easiest, simplest scenario we can talk about here. But what if we have two different nodes? They're geographically distant. Let's say it's a wide area network. Each node is in a different campus, and we have my pod on this node and my pod on this node. And I want my experiment to connect this pod to this pod. Well, then I can still use Multus to create my own network attachment definition. I can peek through an interface that is on the node to the pod and use that interface. But then the missing link here, or the missing path here, is having the actual network traffic plumb through from this node to this node. This is where ESnet sense comes in. So ESnet sense allows us to provision an L2 path between two Nautilus nodes. And of course, it allows us to do that by dynamically configuring a VLAN or VLAN range to use the interfaces across the networks. So what that translates to is that if I use ESnet sense, I can have a VLAN tag that on the interface on this node, and the same VLAN tag on the interface on this node, and I can have those two nodes talk to each other. And if those two nodes can talk to each other over that VLAN, and I provision that VLAN, the beauty of ESnet sense is that it creates the VLAN interface itself on the node. and which means it's going to have a VLAN interface on this node, a VLAN interface on this node, and these two VLAN interfaces can directly talk to each other. They have a very direct L2 path that users can use without having to know what the VLAN tag is, or if there a VLAN tag to, is there a VLAN tag or not there to begin with. And the other beautiful thing about ESNet Sense here is that not only does it orchestrate the path and provisions it for me and monitors its status, but it allows us to have quality of service and guaranteed quality of service in that L2 path. And once we have that path, and we have those two interfaces. This is where Multus again comes in to allows us to peek these VLAN interfaces onto the pods themselves. And we're going to be going through an example that does that shortly. And by doing so, we have an experiment that is across a wide area network that can bring together all those interfaces and conduct any sort of networking experiments that we want. Of course, this is not limited to just traditional network interfaces and traditional network interface cards. This is where all our SmartNIC talk comes in. Using the combo between ESNet Sense and Multus, not only can we leverage ConnectX-6 interfaces, we can also use our Bluefield cards, and more importantly, we can use our Alveo U55C FPGAs to do so as well. And another thing to mention here is that we also have on the cluster three Xilinx SN 1000 FPGAs that are also NIC/SmartNIC capable and also P4 programmable and available for users to provision for their experiments. And to talk more about DSNet Sense, so like I mentioned in the beginning, originally in the original tutorial, it was presented along with Justas Balcas from ESnet. Uh, and he's one of the main people that work on the ESnet Sense project and can dive deeper into what ESnet Sense is and the motivation behind it and the very beautiful experiments that were carried out using ESnet Sense, especially the experiments that use the Fabric Testbed and the National Research Platform, and in many cases both. And in our repository, we have the slides. Of course, we have just this as slides. And one thing here to mention, sort of a shameless plug, but I would like to mention it is that Justice also had a talk called Routed Networks with Performance Enhancement via Hardware Offload as part of the Fabric Testbed webinars. And you can see it on YouTube here. I provided you with the link and the title. If you don't want to type out the link or copy it, you can just copy Routed Networks with Performance Enhancements and should show up as the first suggestion. And Justice there talks dives deep into what ESnet Sense is and how to effectively use it. In terms of using it purely on Nautilus and on the National Research Platform, we have written our own Kubernetes operator that allows you to provision ESnet Sense paths without having to know what the ESnet Sense is, how the orchestrator works, and so on and so forth. So essentially what that allows you to do is write a very simple YAML that basically details what the path is. So this is a simple example here. We created our own custom resource called sense path. So this is me creating a sense path. This is my YAML. When I use kubectl to apply this YAML, it starts a path that goes from, that uses this sense path. Of course, I'm naming it here. I can name it whatever I want to connect these two identifiers. So I'm using node-2-6. This is an actual Kubernetes node here on Nautilus, and I'm using this interface. This interface is the second port that we talked about. So we have the first port that is providing the internet to the node, and we have the second port that is available there for researchers. And of course, this is a 100 gigabit per second port. And we have an identical node called node-2-7. And one key thing to note here is both of them are FPGA nodes, and those FPGAs are SmartNIC capable. So even though my example is using ConnectX-6 interfaces, since you can also use FPGA interfaces and do whatever experiments you want with them. And of course, here I have a bandwidth field. Bandwidth here is not uh, bandwidth per se. This is actually quality of service bandwidth. So whatever number is here, if the path is provisioned correctly with it, that means you have quality of service with that bandwidth. And 1,000 here means 1 gigabit per second. So I'm using 1% of the NIC's capability and bandwidth. And VLAN tag here, this is I can either specify it or leave it empty or not include it at all. I'm setting it here explicitly to 3115 because it makes defining my NAT easier, because in my NAT I can explicitly say 3115. If I don't set it, it's going to be set to something arbitrary that is available. And from there, I have to look at what that thing was. And of course, I can look at my sense path and it'll tell me what VLAN it had used with the orchestrator. And then I can use that to define my multis network attachment definitions. And of course, testbed integration, like we said, doing so and using ESnet Sense allows us to use other systems, other ecosystems, other environments, like the Fabric testbed. For those of you who don't know what the Fabric testbed is, it's an experimentation testbed. So it's a large pool of network experimentation, hardware and research infrastructure, hardware that is, of course, designed to support networking and computing. So very similar to how the National Research Platform is essentially an ecosystem that pools hardware resources from multiple sites and that are geographically distant on multiple campuses. The Fabric testbed also has many resources that include Xilinx Alveo U280 FPGA on each Fabric site, which are there's 23 of them. Those U280 FPGAs are very similar to the U55Cs we have, and both card models are P4 programmable. Both are compatible with the ESnet SmartNIC tool stack, and both are 2 by 100 gigabit per second SmartNICs. And lastly, both models are also fully DPDK compatible. So by using both environments, I have access to a much larger pool of FPGA SmartNICs that can be used for my experiments. As you can see here, on the left side here, we're listing like the ones that we had in blue in the previous slide, that list the FPGAs that are flashed in the SmartNIC image. And you can see all of them are here at SDSC, so they're at UCSD. And you can see here I have all of my Fabric sites listed. As we said, each one of these sites has an FPGA. Also, all of these FPGAs are already flashed with the open NIC shell image, so they're also already available without any sort of flashing to be used as SmartNICs. And of course, both Fabric and the National Research Platform provide detailed documentation on how to use the ESnet SmartNIC as well as ESnet SmartNIC, the official ESnet SmartNIC documentation. And you can see here the common factor here, the most obvious one is the fact that there is a Fabric UCSD site and there's the NRP UCSD nodes at SDSC. So we use what is called a facility port that allows us to use the ESnet allows us to use the ESnet sense to provision the path that can carry out traffic through an L2 path from, let's say, an FPGA on Fabric to an FPGA on NRP without the user and experimenter having to understand what's going on and understand the infrastructure and the underlying architecture behind it that goes into provisioning these paths. This is, of course, thanks to having ESnet Sense. And like we mentioned, we're going to have future Zoom tutorials on how to use that effectively. And now just to show you a very simple, very easy hands-on example, just gonna go to my browser here. This is our repository, so it's github.com/nrp-nautilus/6nrp-smartnic. As you can see here, so just walking you through the repository real quick. So you can see here we have our slides are right here, programmable network and testbed integration. These are our slides that I just showed you, and sense.pptx are of course Justas's slides. Please go and check them out. They go step by step into explaining what sense is and why it's useful, what sort of use cases it allows us to do, what sort of experimentation have been carried out by Justus in using ESnet sense both on Fabric and on NRP and more generally on ESnet. So please check it out. And we also have two Jupyter notebooks here. The first one is a multi experiment on one node. The second one is a sense experiment on two nodes. So I'm just gonna go through the first one here in our tutorial to show you the simplest experiment that you can carry out and start using Multis and carrying out network experiments on Nautilus. Now since this is a Jupyter notebook, you might be more comfortable using Jupyter on your own computer locally. I'm just gonna show you something else we have here, which is Jupyter Hub dash West. So this is our if you go on to jupyterhub-west.nrp-knowledge.io, this is our publicly accessible and publicly available Jupyter Hub deployment. Uh, you can easily use your campus single sign-on and provision your own Jupyter server. As you can see, I'm using the Sulky's desktop one here. You can see it has a remote desktop environment. If I click this button here, that's going to start in a new tab. And of course, the beauty of Sulky's is that it's audio supported as well. And if you provision a GPU, it's going to be GPU accelerated in terms of remote access and streaming. But we're not going to be using that in the context of our tutorial. We're just going to be using a simple tutorial for networking. What we're going to do here is so you can see our README explains a bit of steps here and how to conduct the experiment. But our main thing here is that we want to clone this repo to use the notebook. So if I copy my cloning code and if I go onto my Jupyter Hub, type git clone. Sorry, let me just clean up, then clone it from scratch. You can see here, I refresh, here it is. So 6nrp-smartnik. This is our repository. So this is the experiment we're going to be carrying out. So in this experiment, what we're going to do, we're going to go step by step. So first of all, I'm going to be using Kubernetes from inside Kubernetes. So my Jupyter Hub is running on the cluster itself. And from inside it, I'm going to pip install Kubernetes, which installs the Python library for Kubernetes. And I'm going to be importing all my libraries. You can see here, I have to define three important variables here, which are the Kube API server. This is of course, the Kubernetes server or the controller node. This is where you access it. This is provided in your config file where you sign up for Nautilus. If you're not currently a Nautilus user, please go to portal.nrp-nautilus.io. Let me just type it out so you can see it. So it's portal.nrp-nautilus.io. Sign up for an account. You can use your single sign-on to access the cluster and use all of our resources. And from there, you can become a part of a namespace and use your own namespace. And then you wouldn't have to use this token here that we're using. You can instead use your config file that is provided from the portal. But for the sake of this tutorial, we're going to be using our token here, or we're going to be using the 6nrp namespace. If what I mentioned if you're not very familiar with what I've just mentioned, please check out the Kubernetes Nautilus tutorial provided by Mahadar on Tuesday at 1 p.m. We have the slides and the recordings available, so please check out the tutorial so you're comfortable with using the cluster and all the resources it has, and so you can more easily follow the steps that we're going to be doing here, because we're going to be mentioning some Kubernetes resources like pods and Multis and other things that might be very beneficial for you to have more familiarity with Kubernetes. So after I've defined my variables here, I'm just going to test my connectivity. So I'm uh, finding V1 as my Kubernetes client. And I'm just trying to see if this code runs without any issues with the token that I have. That means everything is successful up to this point, and my Kubernetes library is configured correctly, and my token and namespace, I'm sorry, my token and my API server are defined in a valid way. Now I'm gonna define my Multis network attachment definition. So you can see here, this is JSON. Of course, you can apply JSON or YAML for your own network attachment definitions using kubectl, and feel free to use this as an example. You can see here, I'm calling my network attachment definition bridge-net, of course, in my 6nrp namespace, and it's defining a bridge network over the node that is going to be on. One thing to note here is that I'm not explicitly setting what the node is with Multis. You never have to do that. And that means whatever pod I launch that uses this net is going to have a bridge network over it at the node that it lands on. Of course, you can see here we're setting our subnet range start and end. So it starts at 100 and ends at 200. Of course, from 192.168.1.100 up to 200. And when I provision a pod that uses this network attachment definition, is going to have an IPv4 address that is in that range. Of course, I'm just defining my manifest here. When I apply it, of course, I'm going to try accept in case there's any errors. You can see when I'm applying it in my namespace. And my body here is the manifest that we wrote. And it created successfully, which means we didn't run into any issues. And so this is my terminal window. If you're not familiar with the canines, like we said, please watch the Kubernetes tutorial video recording. You can use the canines here as a simple way of showing you your Kubernetes resources in your namespace. So you can see if I type colon, then NS6NRP. This means namespace 6NRP, and I hit enter. This will take me to my namespace. Here it's 6NRP. I want to look at network attachment definitions. Right now it's showing me pods. Again, I hit colon, then I type in net dash attach dash def. And if you hit and tab, it'll autocomplete. You can hit enter, and you can see here, since it's showing in blue, that means uh, it got defined correctly, no issues whatsoever. If you hit D, you can see its description. Escape takes me back. And we're gonna continue with creating my pod. Similarly, very similarly, we have our pod manifest. You can see here the kind of resource I'm creating here is a pod in my namespace. And of course, name, I'm leaving it here empty so I can later use the same manifest to create different pod names. And I'm defining it so I'm using the node selector to select the host. In my case, I'm using node-2-6 for my experiment. So I'm creating two pods on this specific node that I'm going to be pinging. That's sort of the simplest experiment that I can show you here that you can reproduce. But of course, going from here, we can create more meaningful, more elaborate experiments and even use experiments on different nodes. You can see here, I'm using a service account name called SmartNIC. You never have to define this. And when you're reproducing it in your own namespace, I'm just using here for the sake of having it work with the token that we have provided. And of course, I'm creating a container. So each pod has a container or at least one container. And my container, I'm calling it ping-container. Of course, the name is arbitrary. It's using the BusyBox. The reason for using BusyBox as opposed to Ubuntu or a different image is that BusyBox comes with ping pre-installed as part of IP util. So you can ping using from the pod without having to install anything. And command, of course, this is our entry point. What it runs on start is that it sleeps for 3,600 seconds. So that means the pod will automatically shut down in an hour. We don't want to have it linger forever. And an hour is much more time than we need. Of course, security context is privileged. What this means is that you're running a privileged pod that, in terms of context, has a very high level of access to the underlying node it is being provisioned on. And of course, we need that because otherwise you're not going to be able to ping. So ping is in Kubernetes, ping is one sort of an elevated privilege capability. So you need to have that privileged pod to be able to ping from it. And of course, on Kubernetes, on Nautilus, by default, we don't allow privileged pods unless explicitly allowed to provision them. So if you're reproducing this example at home and you'd like to have privileged access to do any part of the tutorial that we're showing you today, please feel free to reach out on Matrix or via email, and we'll be more than happy to assist you in conducting your experiments. Now, if I run this, I have my manifest. Now I'm going to be creating two pods, so pod-A and pod-B for using my namespace. So you can see here, you can see I'm changing here the metadata name to pod name in each one of the loop iterations. And when I apply it, oh, you can see here we ran into unauthorized. This is purely by the fact that, see here, this is purely by the fact that our token here is ephemeral. So I'm just going to be generating a new token, and of course you're going to be seeing it here. So the token is for the SmartNIC service account, and the namespace is 6NRP. But you can do this in your own namespace, but you can't replicate it for the 6NRP unless you're a namespace admin for 6NRP. Of course, if I provide my new token here, I'm gonna go through all the same steps. You can see config ran through correctly. Here I'm having an error because my network attachment definition is already defined. So it's very natural for it to fail. You can see here reason already exists. And now if I grade my pod, you can see here I'm getting warnings because of using HTTPS, but you can see pod A created successfully, and pod B created successfully. If I'm looking canines, again, colon, if I type in pods and hit enter, show me my pods. You can see both of them are running in blue now. You can see here, status is running. This is their, of course, this is their IP address, but this is internal IP address. So this is within the cluster. And of course, this IP address is not for the second interface that we're using with Multis. This is for the default network interface that is passed through from the node. Of course, you can see both of them landed on node -2-6. I have my code here that is supposed to wait for the pods to come up, but since both of them are running, see it sleeps for 2 seconds and tries again until they're running, but you can see they're both running now. And I'm getting their IP address. Like you can see, this is their IP address right here. And we're just going to be pinging one pod from the other. So this is very simple code where you can define your own test connectivity function. And you can see here we're pinging -C. So C is short for count 4. So it pings with only 4 packets and then stops so it doesn't keep running forever. And if I run this command, you'll see I'm pinging one pod from the other. You can see here's our experiment. So we have conducted our successful experiment for pinging one pod from the other. And from there, if you're able to reproduce this example, you have one very simple example of network connectivity between pods and how to use that. And going from there, you can go on to more elaborate examples that show you other aspects. And let me just show you this real quick. So we have provided you with another example in case you would like to use it and do an example that has more steps, more elaborate steps that allow you to conduct an experiment between node -2-6 and node -2-7. It's almost identical to the point where you're creating a sense path. So this is our sense path using our sense Kubernetes operator like we talked about. We're setting this node and this node. Once you apply this and it applies, you can then create your own network attachment definitions. You can see here I'm using VLAN, so I'm using my VLAN-3115. Of course, this is a typo here. It should be my VLAN-3116 because I'm using my master. So master here is the master interface on the physical node. Set to VLAN-3116, and this interface on the actual node is started by the sense orchestrator. And same thing here. And when I create my experiment pod, same thing here, but I'm using Ubuntu in this example. You can have your two nodes and you can ping from one node to the other. And bidirectionally also in the way back, ping from the other node to the first node. Because ping from the pod on the node, not the node itself. Just the pod that is being provisioned on the node itself. And very quickly also, since I'm showing you here in the scope of running in a Jupyter notebook, as you can see from K9s or K9s, however you want to call it, once I have my own pod and I hit S, that is short for shell, I am inside my pod and I can sort of run whatever commands I want. For example, ping. And like we said, our command is sleep for an hour. So in an hour, this pod will die. If you'd like to conduct more longer experiments, you can always have it sleep for longer. And this concludes our tutorial. We have shown you a basic example of using a multi-attached interface and pinging those interfaces on a Kubernetes node. Please feel free to reach out if you have any questions. And like I had mentioned, we're going to be having a future tutorial on using FPGAs as SmartNICs, and it's going to be somewhat longer than this tutorial. It's not going to be just basics, and we're going to show you how to provision those FPGAs, how to simulate their behavior, how to write your own P4 logic, how to apply that logic onto PCAP files for testing, and having software emulations and hardware emulations before actually running on the actual hardware. And from running on the actual hardware, how to provision those paths with the sense operator, and how to use FPGAs with FPGAs to conduct whatever experiments that you have. And we're going to be showing you a very small example where we have implemented segment routing using microSID SRv6 on those FPGAs, and conducted our line rate experiment of 100 gigabit per second using the FPGAs, using our own arbitrary P4 logic. And thank you very much.